Hey everybody, welcome to your Chemistry 1212 Buffers Lab lecture. Let's go ahead and jump right in, shall we? A buffer solution is a solution that is resistant to changes in pH. It's composed of a weak acid and its conjugate base, or a weak base and its conjugate acid. Oh, sorry about that. There we go. All right. So a buffer can make something bad or unsatisfactory better. It changes in pH by reacting with any added strong base or strong acid to create a weaker base or a weaker acid. The acid component of the buffer, which is represented by HA, it interacts with an added strong base, which is your OH, and it's going to produce a weak conjugate base. And you see that here in this particular equation. Now, this thing, I apologize. All right, there we go. All right, so the weak base component of the buffer reacts with an added strong acid to produce a weak conjugate acid, and this is where you see that represented in an equation. All right. Now, by reacting the added strong base or strong acid to produce more conjugate acid or base, the strong acid or base can't drastically affect the pH of the buffer. Small changes in the pH can be observed from the changes in the concentration of the weak acid and base. Since the hydronium ion and the hydrogen oxide are usually, let's say, very small numbers, these numbers are often expressed as the negative logarithms, which are base 10 of the original number. These new numbers are indicated with a P for power of 10. Log 10 of the hydronium ion concentration and the hydrogen oxide concentration are abbreviated pH and POH respectively. Now similarly, the negative log of the acid ionization constant pKa, the base ionization constant Kb is abbreviated pKb. And that's just kind of food for thought when we're moving through this, okay? The ion product constant for water, Kw, is 1.0 times 10 to the negative 14 at 25 degrees Celsius, and the pH and pH plus POH is equal to 14.00. The product of Ka for an acid and Kb for its conjugate base, so Kw and pKa plus pKb equals 14.00, which is 14.00. And I know I'm really saying those out, but what I want you to remember is that those .00s matter. So make sure you're going to the right decimal points when we're actually working in this lab. So you can take that calculation in the other direction as well. You saw one calculation. This is the exact same thing in the other direction. That's all it is. All right, so take note of the correct number of significant figures for these calculations, just as I was saying. As discussed in the absorption versus concentration lab, we talked about it then. It's the exact same thing. So if your number is, then log should be reported to 2 sig figs to the right of the decimal. Okay, so if Ka is equal to 3.3 times 10 to the negative 4, then pKa equals 3.48, which has 2 digits to the right of the decimal. Now, the pH of a buffer can be calculated using the Henderson-Hakelbach equation, and that's what you see here. This is your Henderson-Hakelbach equation, okay? Now, here we can look at an example of that. We're going to calculate the pH of a solution of 1.25 molar acetic acid and CH3COOH and 1.5 molar sodium acetate, which is CH3COONA. The K of acetic acid is 1.8 times 10 to the negative 5. The concentration appears in both the numerator and the denominator of the Henderson-Hakelbach equation, causing the units of volume to cancel out mathematically, which means the number of moles of acid and base can be used instead of molarity as seen right here. Now, this feature is useful in problems where the volume is changing due to the addition of reagent. This also shows that the pH of a buffer is not affected by the addition of water. A mixture of acetic acid and sodium acetate makes an effective buffer. The acetic acid reacts with any added base to form acetate ions and water. The conjugate base, the acetate ion, reacts with any added acid to form acetic acid and water. So you're going to show these reactions in your lab notebooks and handouts, any handouts that we have. It can be nearly a pH value. Buffers can be nearly any pH value depending on the composition of the buffer. As the Henderson-Hackleback equation shows, the pH of a buffer is dependent on the pKa value of the acid component of the buffer. Now, buffers have a limited pH range in which they are actually effective. Okay, the ratio of base acid component in the buffer must be between 0.1 and 10. If the ratio is less than 0.1 or greater than 10, the buffer is quote-unquote busted and will not resist changes to pH. The ratio of base to acid allows for an effective pH range of plus or minus 1 pH unit around the pKa value of the buffer. For example, if a buffer has a pKa value of 3.60, then the effective range of the pH of that buffer is 2.6 to 4.60. Experiment, you're going to prepare an acetic acid sodium acetate buffer solution and the ammonia. The pH of each buffer solution as well as that of the DI water will be compared. The buffer stability of each buffer will be compared when stressed by the addition of a strong acid, which is your hydrochloric acid, or by the addition of a strong base, which is going to be your sodium hydroxide. Now, of course, we have trivia. We're not going to do these. They're not going to be a bonus. Actually, you know what? Let's go ahead and do the bonus. If anybody wants to do the bonus, you guys can write this down and hand it in to me when you come in for the determination of a Ka of a weak acid lab. Number 1, what is the formula for ammonia? Number 2, what are you going to record the volumes to the nearest? Number 3, what do you add to the ammonia in the first part of the experiment? Number 4, how do you calibrate the pH meter? Number 5, how are moles of each aqueous solution determined? And number 6, strong acids and bases do completely an aqueous solution. All right, all we have for the actual buffers lab lecture. If you have any questions, make sure you're reaching out, and I'm happy to help you any way that I can. And good luck on your buffers lab. You guys have a good day.